Okay, so the next slide is the overflows. Overflows are also important because when you're doing multiplication operation in convolutional and fully connected layers, you do incredible number of these operations, and you're adding numbers on top of each other. And as you accumulate these numbers, you get many big results. And these parts are also called accumulators because that's where we sum everything on top of each other. Okay, however, you're using a limited precision when you're trying to quantize your network. So due to the limited dynamic range of your format, you're using integer 8 or integer 16, whatever. If you use the same bit width for weights and actuations, and when you sum them up, because the accumulation occurs something like this, you're multiplying the weights with some inputs and actuations, the actuations of the previous layer, and you are summing them on top of each other. And if you use a bit width for these values, when you sum them up, if you use the same bit width, the bit precision of this accumulator will not be sufficient. This is called overflow, exceeding the largest representable number of your format. You sum them up and you cannot represent numbers. What does it mean to represent a number in a precision? Imagine we have 16-bit fixed point precision like this. We are using a single bit for sign because they are negative and positive values. We are using 5 bits for the integer part, mantissa, and 10 bits for the exponent. That means you are using 0 and 1s, minus and plus for the first most significant bit. And you are using 5 bits here, and you are using these values, guys. And actually, this number is this number. This is the largest and smallest number you can represent. Imagine this range, the dynamic range, can cover your dynamic range. Okay, let's see what happens when overflow occurs. Okay, that's why when you implement an accumulator, you use more bandwidth for the integer parts. How you do it? Well, you are multiplying two n-bit numbers. When you multiply them, you need two n-bit numbers, because those two n-bit numbers could be the largest numbers, and when you multiply them, it's like squaring them up. The square of an n-bit number needs two n-bit precision. Okay, so in a single filter of a convolutional layer, the accumulated multiplications are c times k squared times. So c dot k squared times multiplications you do, where c is the number of input channels, the depth of the input, and k is the kernel width. So I'm assuming that it's a square kernel, so it's k square. So to avoid overfitting, your accumulator should be of size 2n plus m, where m is, as I noted here, at least this value. So you have to increase your precision. So there's a nice example how you increase your precision, increase your bit width for integers. You lose exponent precision. I mean, this is not exactly 2n plus m example, but you have 16 integer precision for weights and activations, and imagine you are using 5 bits for mantissa and 10 bits for exponent. Well, you could increase the bits you use for mantissa and decrease the bits you use for exponent, which means you will lose precision, but you are going to gain a larger value for the integers so that your accumulator will not overflow. That's also something you should always keep in mind. Am I overflowing? I'm adding on top of something, multiplying things with each other. I'm adding them on top of each other. So when you use 8-bit precision, it is not as easy you do in the example of the previous video. So you have to keep in mind what is the result of the multiplications. That's why there is this concept of overflow in the accumulators. Okay, so let's get back to the example we have covered, the pre-trained weight quantization. Just like we did in the previous week, taking a model trained for single-bit precision and directly quantizing it to, for example, 8-bit integer without any retraining can result in a relatively low loss of accuracy. We have experienced this in the previous video, that cat video was not affected. The probability decreased a bit, but it was still the maximum probability category, and it was okay. So some fine-tuning can further improve the accuracy, and doing fine-tuning on pre-trained weights is a nice idea, and it's a one step to quantization-aware training, which we are going to discuss today. So there's a nice paper here. You should I'm sorry, I don't have internet right now. I'm going to get internet first. Okay, sorry. Let me get my internet. I guess I have my internet. Okay, so let me just connect. So this is a paper. You could download it school because this need IEEE Explore subscription, which you can do at school. So it's called Ristretto. Ristretto is a very nice example. It's a framework for empirical study of research efficient inference in convolutional networks. Well, what we've done in the previous video was an example of an empirical study of resource efficient inference, but they've done it in a more wide. They cover many examples, so I strongly recommend this paper if you're interested in this subject. Okay, and again, just like we did in the previous week, a scale factor is used to adapt the dynamic range of the tensor at hand to the integer format we are using. So we have calculated this scale factor per layer per tensor. Tensor means the weight matrix you're using for each layer, for each weight and bias matrix tensors. We have calculated it separately, but that's the way to do it. So what we've done was the simplest way to do it. We've mapped the maximum and minimum values, the dynamic range, to this integer format. It was 8 bits and 256 values. But for the activations, we did not do this. You could do it or not, but we did not do this. So that was a type of limited quantization or pretrained weight quantization. When you're doing this, we always check the maximum and minimum values. Well, if you check your maximum and minimum values in our slides, you'll remember there was the maximum and minimum values was limited to -1 and +1. The histogram of values were limited to there, and since we do something called regularization, those weights are limited to those values because regularization in optimization will result in smaller weight values. This is something nice for us. You don't know regularization yet because regularization is the title of the previous semester's course, which is 445, this course. I'm just going to this course. For those who have taken this course, they will immediately understand what I'm talking about. But for those who haven't taken this course, regularization is a process during training which keeps the weight small. So you can have, but however, although you do regularization, there could be very big values or very small values in your histogram. Well, they will dominate your dynamic range. They are called the outliers. Those outliers will take the maximum and minimum values to extreme limits. Well, in that case, your quantization will be poor. You will have more quantization error. So you will have you'll need a narrower minimum maximum range. And at some point, maybe you have to ignore some outliers. How to cut the clip, how to cut the histogram? Well, statistical measures can be used. Well, there are nice papers covering this. This one, and this one are nice examples of studying the statistical measures to cover these examples. Just take a look at them if you're interested in handling the outliers in these sessions. And that's also a nice example to do it. Okay.